So essentially, what I was saying is this. Previously, we've been defining an FG module, but doing a general definition for any vector. You define this multiplication for any vector in the FG module and any element G in the group. So, but there's one other thing now we can do. Instead of defining it for any vector, we can define it just for the basis vectors. Then we can use the fact that any vector is a linear combination of the basis vectors to extend it to the rest of the vector space. But if you can define it on the vector space, on the basis of vector space, and after which these four properties are satisfied, then it becomes that vector space is an FG module. As long as these four properties are satisfied on all the basis vectors. Okay. So I think the proof follows. You can go through it carefully. You'll be able to see. I think we defined the trivial FG module. Did we? No, we defined the faithful one. I think we defined both trivial and faithful. So the thing that maybe we didn't talk about is this one, where if you have your multiplication fully defined on the basis elements, you can extend it to the rest of the vector space, turn it into an FG module. So using that idea, we can build another type of module, special type, that is normally called the permutation module. So it's based on this symmetric group, Sn. So pick a subgroup of Sn. So of course, Sn is just the group of all permutations of n symbols, n distinct symbols. Then if we pick a vector space that is n-dimensional, and we set this up as the basis, we have n vectors as the basis. Then for any permutation in the subgroup of Sn, we define this multiplication on the basis vectors. So what this simply means is the following. Again, remember, like we said, this book, instead of writing G of I will rewrite it with the correct notation. I'm rewriting the handwritten notes. I'm done with the first chapter. So I will scan them and share. So instead of writing GI, this book writes IG. But we want to focus on this notation. So that's why I will try to convert this into this notation. So this one says the following: if you pick a vector in the basis multiplied by an element G, which is a permutation, then it's defined as V, then subscript the image of I under G. That's what it is. Okay. We shall do an example shortly. So this multiplication will satisfy these four properties. Because if you follow it carefully, it will satisfy these four properties that will turn the vector space into an FG module. These four properties will be satisfied under that multiplication. The justification for that is here. So once those four properties are satisfied, you can conclude that V now will become an FG module. And this is what we call the permutation module. So let's do an example. So we pick S4. We have a basis, a S4 now means we have to look for a 4-dimensional vector space. We set this up as the basis for the space. So if G, this is the permutation 1, 2, which leaves 3 and 4 fixed and interchanges 1 and 2, right? So under this permutation, you can get the images of each of the other elements. So under this permutation, it takes 1, the image of 1 is what? Is 2. This one we did in group theory. So it should not be new to you. So G of 2 will be 2. What about, it leaves the others fixed. So G of 3 won't move. So we shall use this in our calculation. So I just want to write all of them out first. Then we know G of 4 will also be equal to 4. So only 1 and 2 are interchanged. 3 and 4 remain fixed under this permutation in S4. So let's see, how does this multiplication work? Huh? So if you multiply, pick this basis vector, so V1 multiplied by G turns out to be the same as V subscript, G acting on the subscript here 1. But G of 1 is 2. So this turns out to be V2 and so on. So that's what you have here. If you have V2 of G using the same argument, the same idea, this is V. This is the same as V, and the subscript is G2. Whatever is G of 2, G of 2 is 1. This is a mistake. So this will be equal to V1. So under this multiplication, V2 goes to V1, and so on. So if you have V3G, this one will not move because this permutation G leaves 3 unmoved. It is fixed by 3. I mean, 3 is fixed by this permutation. The same will happen to 4 because 4 is fixed by this permutation. This will just be V4. So is that making sense?
Yes.
Good. So remember, under this multiplication with the 4 properties defined, this vector space becomes an FG module. So what that means is also there will be some endomorphism that is induced where V is any vector is sent to VG. This is an endomorphism of V. It's a endomorphism of the vector space, which is the FG module. But at this point, we are just interested in the vector space structure. So given that it's an endomorphism, you can obtain the matrix. The matrix that represents this endomorphism with respect to the given vector space. So how do you find that? We've seen that now the matrix we are looking for is this one, G. Let's see how we obtain it. So how do you find the matrix? Find the images of the basis vectors and write them as a linear combination of the basis. I believe you have gone back to the chapter on linear algebra. We agreed that you do that. So let's see. What's the image of V1? The image of V1 is V2. But now, once you get the image of the first vector space, you have to write it as a linear combination of the other basis vectors. And you must maintain the order. Remember, it's an ordered basis. So this will give you 0, V1. And then there's 1, V2. This goes on. The other 2 will be 0 also because V2 is just 1 times V2. And The last one is 0, V4. So the first row of this matrix will be this coefficient 0, 1, 0, 0, which is what is up here. So the next thing you check is what is the image of V2? The image of V2 is V1. That means the coefficient of V1 will be 1, the rest will be 0. What is the image of V3? It's V3. So V3, the coefficients of all the others except V3 will be 0. The same happens with the last one. So this gives you the matrix of this endomorphism with respect to the basis V1, V2, V3, and V4. So you do the same for this one. H now is still an element in S4. So again, it's important to know the images of every element. So what does H do to 1? H1 is what? Where does H send 1? You can hear me?
To 3.
So H will send 1 to 3. Because it leaves 2 fixed. We'll send 3 to 4. And also it sends 4 back to 1. So using this, you can get the images of each basis vector. So V1H is V3 because H sends 1 to 3, right? V2H is V2 because H sends 2. Is the font small or you can see clearly?
We can see clearly.
Okay, I've enlarged it a bit, so hopefully that is better. So we do the same for all the others. Then now you have to write V3 as a linear combination of all the basis vectors. But V3, if you write it as a linear combination, what will that be? It will be 0 V1 plus 0 V2. This keeps going on. And 1 V3 plus 0 V4. So if you want the matrix with respect to this basis, or at least the first row of the matrix, it will be these coefficients, 0, 0, 1, and this is what they are here. So now with respect to H, this map, this endomorphism defined by V being sent to VH, the matrix that represents this endomorphism is this one with respect to this given basis. So this shows how the permutation module works and how you can find these matrices for the linear transformations. So here is the definition. It says if G is a subgroup of Sn, the FG module with a given basis with multiplication defined by this is called a permutation module. So here we don't need to know what the basis is. It's just we know that it's an n-dimensional space. And therefore it must have n vectors in its basis. So the interesting thing about this is anytime you act, you multiply, you do this multiplication on a vector in the basis, you only get one other vector in the basis. So that means the coefficients in any one row will be all zeros except one of the vectors, the one which is the image under this transformation. So such a matrix where there's only one, where one appears only once and the rest are zeros is called a permutation matrix. So how you get a permutation matrix is simply by rearranging the rows and columns of the identity matrix. If you reorder them, you get a permutation matrix. That's another way of defining it. So, one thing I'll mention, you can extend this to any other vector in this space by simply using the fact that any vector in that space can be written as a linear combination of the basis vectors. So if you have it in this form, then you can extend this multiplication any other vector in the if you write it like this, then you're able to extend it. Again, the rest tells us that this is a faithful it's a faithful representation because it's only the identity element in the group that fixes all the basis vectors. So that basically what it's saying is that Vi multiplied by G will only be equal to Vi for all the basis vectors if G is the identity in the group. Without this, because that's the only one that will fix every element. And by fixing every element, therefore it will fix any other vector because any other vector will be a linear combination of the basis vectors. So this makes this a faithful. So your conclusion now will be that for any other vector, the only way this can happen, Vg equal to V. This can only it's only true if and only if G is equal to the identity element in the group. That makes it a faithful FG module. So this, the next example here, which tries to illustrate the concept of the FG module, the permutation module. So we pick the cyclic group of degree 3. Think of it as a subgroup of S3 because S3 has a subgroup of order 3 that is made up of the rotations. That is, it consists of E, A, and A squared. Think of it as the rotation through 120 degrees. So this is a subgroup of S3. It's a permutation group. So when you're working in S3, we have to work with a three-dimensional vector space, which will have three vectors in the basis. Using this, maybe we should write all the elements of S3. A itself, you can think of it as this cycle. One, usually there's no comma. 1, 2, 3 in S3. And then you have A squared, the only three elements here. So this one will be 1, 3, 2. I think that's the only other cycle. What about then the last one is the identity, which normally denoted by this, fixes everything. So these are the three permutations that can be put here. A cyclic group of order 3 as a subgroup of S3. So we use these permutations on all the basis vectors. So the identity will fix all of them. So V1 is V1 and 1 give you V1 and so on. Identity will fix all of them. It doesn't move anything. So V1A will be equal to V2 because A takes 1 to 2. V2A will be equal to V3 because A takes 2 to 3 and so on. V3A will be V1. So you can get the images of all the basis vectors under this. So now, given any other vector in the space, you can get its image using this. You can extend it to any other vector in the vector space using this now. At this point, you just define everything on the basis vectors, and you can extend it to any other vector. Is that making sense?
Yes.
So I think we also
Excuse me, Doc.
yes.
Kindly let Janet in.
She's admitted. I think we talked about this last time. We just covered the part that was missing. I don't hope you've gone through this. If you have any questions, of course, you can ask. So we complete chapter 4. So the other parts I think that we missed was this talking about the submodules. I suspect parts of it we missed. We did some parts and the other parts were not in the notes. But like I said, I'm rewriting them because the ones I have some missing things. Okay, so I will go back so that we talk about the submodules. So I had given you the definition of a submodule. Someone's microphone is on. Whose microphone is on now? I think it's off now. Okay, so we have this FG submodules. So an FG submodule is just a module. Remember, an FG module is a vector space. So an FG submodule will just be a subspace of the vector space with one extra condition, that this multiplication is preserved. The multiplication that makes it an FG module is preserved when you restrict yourself to the subspace. So a subspace does not have to be an FG module. It can fail actually to be an FG module. It only works if this multiplication, this property, the multiplication is preserved and stays within the subspace. So this is a summary. It's an FG submodule will simply a subspace of V, which is also an FG module. That's another way of defining it. There are two equivalent ways. So this example says for any FG module that you have, there are two submodules, the usual suspects, the whole space and the subspace that contains only the zero vector. This will be your most natural examples. So this is a permutation module that we defined earlier, right? It even says here, the previous example, there's this permutation module that we defined earlier. So the claim is that if you pick W, you pick W with this vector, which is the sum of V1, V2, and V3. So what is the claim? The claim is that this is we should be able to show that this is it is a subspace. Of course, the span of any vector is a subspace, but we need to show that if you have W multiplied by G, you should always stay within the span. You don't get out. So this is the only thing we need to show to confirm. But from your linear algebra, the span of any vector or set of vectors will be a subspace. So as a subspace, that is fine. As an FG module is what we need to confirm. If we confirm that it's an FG module, then it becomes an FG submodule. Remember, we already determined these permutations. One was just the identity. A was the permutation 1, 2, 3. This was A. And B, sorry, A squared was a permutation 1, 3, 2. So W1, of course, will naturally be W. The reason that will be the case is the following. What will happen is, since W is the sum of all these three vectors, this permutation acting on any one of these, this vector multiplied by any one of these elements will simply be a rearrangement of the same vectors. So you'll never have a different expression. You'll just be rearranging the same vectors. So all these multiplications will just give you W, right? Any of them will give you W. So these multiplications don't get you outside the space because W was already in the space. So the span of this vector, this new vector, is a FG submodule of this space. So this vector, the span will be an FG submodule. So the next one we look at is an example which fails to be an FG submodule. So as a vector subspace, that works because we have a new vector. We create it as a sum of these two vectors from the basis. So this new vector acting on A gives you V2 plus V3. But now V2 plus V3 cannot be written as a linear combination of V1 plus V2. right? The reason for that is that all these are vectors from the basis. You can prove this. If you have, we just work with a small, suppose we have V1, V2, and V3. Then if I create a new vector, say V1 plus V2, I cannot write this as a multiple. I cannot write this will not be possible. You can prove that for yourself. Now, if I have the vector V2 plus V3, if I try to find this constant, I will land in trouble. This will never work. As long as these are basis vectors or a set of linearly independent vectors, then this will hold. I cannot write this as a linear combination of these two. So in other words, this vector will not be in the span of this vector. That is exactly what happens here. V1, V2 is our vector. When it acts on A, we get a vector which is outside the span. And therefore, this subspace fails to be a submodule. Is that making sense?
Yes.
Is it only making sense to Makeba, or the others are also understanding? Or we can assume Makeba is now official spokesperson. You're responding, so I don't know whether it's making sense to everyone else. If there's something not making sense, you can ask. Okay. And please, these things can be very confusing. You have to go back and read them carefully. You have to put quite a bit of time in them for them to stick. You can walk away thinking you've understood, and next time you look at it, it looks entirely strange. So try to spend more time on them, and a lot of repetition is necessary. So the next thing we'll look at is the irreducible FG modules. Again, we may have a bit of this, or rather the part that comes after this, but not this one in particular. So but though I define an irreducible FG module, one, it must be non-zero, so you can't have just a zero module. And then the only other submodules will be zero and the whole space. It can't have any other submodules. There are no submodules which are proper subspaces. But if it's possible to find a submodule which is not zero and neither is it the whole space, or rather a submodule that is properly contained in the vector space, if this is possible, then we say that the FG module is reducible. So you need to understand that as well. So you can extend this idea of irreducible FG modules to a representation as follows. So you define, remember this FG module that we defined using Fn. So we'll say that the representation will be irreducible if this FG module is also irreducible. And also we'll say the representation is reducible if this corresponding FG module is reducible. So here is a claim that if W is reducible, is a reducible FG module, so it means there's a smaller subspace, a proper smaller subspace. which we call W. That means the dimension of W will be strictly smaller than the dimension of V, because this W is a proper subspace. It's smaller than V, and it is a subspace of V. I mean, it's contained in V and it's a subspace of proper subspace of V. So its dimension cannot exceed that of V, cannot even be equal. So it will be strictly less than. So if you take a basis of W, because W is not the whole of V, the basis of W, let's say it's W1, W2, keep going until you get to WK. So this will be a set of linearly independent vectors in V. So anytime you have a set of linearly independent vectors in V, if it is not yet a basis, you can always extend it. You can extend it to a basis. So I could call this one VK plus 1. Assuming it's an n-dimensional, this will go all the way up to Vn. But this set of vectors are the vectors that are outside W, right? Because this is a basis for W. So you can extend by a set of linearly independent vectors that are outside W to get a basis for the whole space. So this, if you call this one B, this basis that is created by extending the basis for W, then the matrix again will look like this. We did an example of this earlier for direct sums. That was last time. In this case, we are not looking at direct sums. So I will to get the matrix. So for instance, remember, if you want to get the matrix G with respect to the given basis, it means you must get the images of every basis vector, right? So if you take the image of W1, will be W1G, but remember it's a submodule, right? So W1G will still be a vector in W. And if it's a vector in W, it can fully be expressed as a linear combination of the basis vectors in W. So in other words, the coefficients will some of them will be non-zero for W, and so on. So this will go on until you get to WK, lambda K, and then WK. So again, it was a subspace, so it has its own basis. If I want to get an element in the subspace, I can write it as a linear combination of my basis vectors of a subspace. But now here, I want to think of it as part of, this is a basis for the whole vector space. So I'm thinking of this as the map from V to V, right? So that means I have to extend this to the other vectors that form a basis for V. If I extend this, then the rest of the vectors will have zero coefficients. So this will go all the way up to 0. So this goes on, this will be the same from W1 up to WK. And all the others in between will behave the same way. This, instead of W1, maybe I should write W11 to W1K. Then WK1, W1 keeps going like that. So then we'll have lambda KK, WK. So up to this point, the only vectors that I need are the W's. All the others will have zero coefficients. So this matrix, this K by K matrix here, will be this XG. Then the other zero coefficients will be the ones that come here. So after this, what follows are the vectors VK plus 1. But now VK plus 1 I can't tell what its coefficients will be. Some may be 0, some may not be 0. If it acts on G, definitely it will not be in W, because Vk plus 1 is outside W. So Vk plus 1 G cannot be in W. So what it means is that since it's not in W, I will need all these vectors, or I may need all of them, not necessarily need all of them, but I may need all of them. So now the coefficients would be, say, B1, W1, all the way up to, I will need all of them. And I can't tell whether they are 0 beforehand or not. So these coefficients will form this bottom part. You keep doing this until you get to Vn. So these coefficients, beta ones, all the way up to the last one that will appear here, will form this bottom part of the matrix. So you have used the fact that this is a proper subspace. Its dimension is less than V, and therefore you can extend its basis to a basis for the whole vector space. And when you use this now as your basis, your matrix will look like this. Only if you use this as your basis. If you use a different basis, then the matrix won't look like this. Is that making sense? So I encourage you to see, like what I've done here is expanding this content. If you read it the way it was, these things are not clear. What I'm writing down is not clear. So as an exercise, you should go back and write it out fully, explain this. Here it is just done like the gospel truth. The way it's written here, it doesn't give you the details of how this is obtained. So I've tried to give you the details. Try to go and sit down and write out all the details. Because I expect you to be able to write out the details. I don't expect you to just give me such a matrix and walk away. I will need these details. So if it's not making sense, you ask so that you can write it out fully. But I hope it makes sense. Yeah. So all this is just explaining about so there's one more exercise you can do. This last part, you can take it as an exercise. See this one. It tells you that if you set up this map where G is sent to XG and G is sent to ZG, this gives you two new representations of G. So there's a brief explanation here, but it's not complete. Now you have to expand it. So these two maps, it gives you two representations of lower dimension, of lower degree rather. So anytime you have an irreducible representation, a reducible FG module, you can always extract two new representations out of it. Sense. So, but essentially try to expand this. If you write it out and you think you're done, you can share so that I look at it. If you are satisfied with your work, then you don't have to share. But you can, if you write it out and you want me to look at it, you can share with me. So here are some examples. Let's try to go through this one. So we have the cyclic group, degree 3. Think of it as a permutation group, so that these are the images of V1, V2, and V3 under A. So this matrix for A if you write out this matrix, it's what? V2 will be what? 0, 1, 0. V2A will be what? 0, 0, 1, because V2 goes to V3, and V3A will be 1, 0, 0. This gives you the matrix for this A with respect to this basis B. So maybe I should indicate that it's with respect to the basis V1, V2, and V3. So earlier on, we found a submodule of this FG module. And that submodule was the subspace of V that is spanned by these three the sum of these three vectors. So this is just one vector written as the sum, as a linear combination of V1, V2, and V3. This was our small vector. We called it W. The span of this vector gives you a subspace, which is also a submodule. So you can, this being one vector, V1 plus V2 plus V3, I can extend this to a basis of the whole vector space, right? So this is one of the vectors in my basis. I can extend this, and you can confirm that this first vector will be linearly independent will not be dependent on the other two. So this new set is a set of 3 linearly independent vectors. The dimension of my vector space was 3, so this automatically becomes a basis for my vector space V. So now I can create a matrix for A. Okay, let's do it for just A alone. So call this first vector W. So WA will just be equal to W, right? So since W is a first vector here, it means I can write this as 1W. The others will be 0. 0 V2 plus 0 V3. So I need to check V2A. What is V2A? Was it V3?
Yes. Yes.
So then I need to write V3 as a linear combination of these basis vectors. So if you look at it carefully, it's the same as W minus V2 minus V3 minus V1, sorry. Just hold on. I'm looking at the wrong one. V3 will just be V3. So V3 is simple. V3 is already here. So all these first two will have coefficient 0. So these first two 0 times W plus 0 times V2 plus 1 times V3. So the last one is V3A will be equal to V2. But if you look carefully, you will see that V2 is the same as W. For V3, is it V2 or V1?
V1.
It's V1. Now you write V1 as a linear combination of these 3 vectors, which will be W minus V2 minus V3. So these coefficients are the ones now in the matrix here. With respect to this basis, this is the matrix that represents the endomorphism, which takes every vector and sends it to VA. Right? So if you take the coefficients, you can see 1, 0, 0. So 1 up here, 0, 0, 1. So now we remember W was a one-dimensional space. So this matrix here will just be 1 by 1. W has only one, this subspace W has only one basis vector. So that's it. So that's where this one will be your XG. I think this one was ZG. Now this matrix here will be the ZG you're looking for. So under this, we said this will just be the trivial representation where you have the map from, let me just use the whole group here. This first one will just be the representation from, which is an homomorphism from G, the general linear group. It's just the field itself, F, because it's a 1 by 1 matrix, it's like the field itself. So everything will be sent to 1. Every element here is just sent to 1. That's what this first one representation will be. The second representation will be determined by this one. Where send to the general linear group of degree 2, because now we're having 2 by 2 matrices. And then the matrix for 1, the matrix for 1 will be this one here. The matrix for A, for 1 will be sent to the identity. A will simply be sent to this matrix here. And A squared will be sent to this matrix here. So under that setup, this becomes it's a homomorphism, and therefore it's a representation. So here we have, out of the first representation, or rather out of this, we've been able to extract 2 representations. We didn't start with a representation, we just started with the F permutation module, and out of that, we've been able to pull out 2 representations. Is that making sense?
Yes.
Okay, so the spokesperson has agreed. Actually, it's here. The representation we are talking about is here. The first one is not exciting because you have only one element here. You could look for more examples where you'll have a more interesting matrix to look at here. So let's look at the next example. Here we work with the dihedral group, the symmetries of a square. We take F2 as our FG module. So this we already described earlier. where I think A was sent to, A was going to which matrix? I can't remember. Is it 0, 1, minus 1, 0? Was that correct?
Yes.
Yeah. So if I have VA, we defined it as V multiplied by this matrix, 0, 1, minus 1, 0. So since this is the image of A, that's how we define the representation. So any vector, if you pick any vector in what? In F2. If it acts on A, this is what you get, because you'll multiply this vector by this matrix. So this is what you will get. If you let it act on B, again, you'll multiply. B is sent to a different matrix. So B was sent to what? I think B was sent to, I think it was 1, 0, and 0 minus 1. Is that correct?
Yes.
So for B, this is what you will multiply with. Any vector you pick from the vector space acting on B will be sent to lambda minus mu. This will be its image. So this is how you'll define the linear map. So the claim we make here is that V will be an irreducible FG module. So in other words, we claim that there's no, for this as an FG module, this F2, it will be reducible. In other words, you can't find a subspace which is a submodule. Now we are lucky because we are working with a two-dimensional space. So any proper subspace will either be the zero subspace, but we are not interested in the zero subspace. The other option should be a one-dimensional subspace, right? So basically, we will be forced to look for a one-dimensional subspace if we want to find a submodule. So we work with that in mind. So we assume we have a one-dimensional subspace, so it's spanned by one vector. This one vector is this one, consisting of the two elements, alpha and beta. So the claim is that it's an FG module, but that means that if alpha B acts on this vector, you should get another vector that is a scalar multiple of beta, because for it to be a submodule, this multiplication must give you another vector within the same space. So, but if you do that, it means it forces alpha to be zero. The only way that can work is if alpha and beta 0. You can see that as follows. So let's try it out. If alpha B, if this is an FG submodule, if you have a one-dimensional FG submodule, then alpha B is equal to, this is what B does. You'll end up with alpha and minus beta. But for this to be in the space, it must also be a multiple of the spanning vector, right? So try to solve this. This gives you, it means alpha should be equal to lambda alpha, and it also says now the only way this can happen is what? Since lambda is some non-zero scalar, this can only happen if alpha is 0. The other one says that minus beta should be equal to lambda so if you solve this, I think you should get both alpha and beta are 0. Is that correct? Have I missed something? So from this case, alpha will be forced to be 0, right? This one may not be 0. From this part, beta itself may not be 0, but this first one will force us alpha to be 0. Is that correct? So the second one again should force either one of them to be 0. The second one again, if alpha b on A is equal to, so if this acts on A, this is what you get, minus B alpha. So then this is supposed to be within the same subspace, so it must be a multiple of the spanning vector, which is alpha, beta. Again, I think if you try to solve this, you have minus alpha minus beta. Then minus lambda alpha will be equal to 0. Then the other one is what? We'll have so we have alpha, positive alpha will be here. Because alpha is positive, this one moves, minus lambda alpha will be equal to 0. So you need this system to be satisfied. So that system, eventually, if you work this out, you should get that the only way this will be true is if both alpha and beta are 0. I'll leave the logic to you, but I've given you the ideas to work with. So once you work this out, you should conclude that this can only be true if both alpha and beta are 0. And that means you cannot have a one-dimensional subspace. Any one-dimensional subspace leads us to a contradiction, that the only vector in that subspace is the 0 vector. So you can't have a one-dimensional subspace. You can only have the 0 vector or the whole space F2. So as an FG module, F2 here will be irreducible. And also it means the representation that you are working with here will also be an irreducible representation. So we have looked at two examples, one that is reducible and this second one that is irreducible. Try to sit down and work out the details for this. If you sit down long enough, you will see that the only conclusion you can come to is that alpha and beta must be 0. So this is just a summary. So remember, at the end of every chapter, you have a lot of exercises. So the assumption is that you are trying to solve these problems. Now, the good thing about this book, the solutions to the exercises are at the back. So and some of the solutions are a bit sketchy, the ones that are given. So for the sketchy solutions, you have to flesh them out, give them some more substance on your own. Don't just copy the solutions. Some are very brief. They don't explain everything. They're more like hints than full solutions. So if you are asked to answer these questions in an exam, you must answer them fully. You can't give the hints as the answers. So we can take a 5-minute break. Mtaki kupumzika.
And just continue from my side.
Okay. So we have to go to, I think this is the other topic that we were supposed to cover. Group algebras. So this one now again requires you to put on your thinking hat. It's going to introduce some new ideas. So what is a group algebra? The first thing you do is you have a finite group. So you're able to list all the elements of the group. In this case, assume they are n. Once you have a finite group, you construct elements like this. This is what the elements we want will look like. So you will not be able to write it as just one element. The only thing that will be changing are these coefficients, lambda 1, g1, lambda 1, gn. So this multiplication does not have to make sense, but this will be an object now we construct, and we leave it as it is. So this will be an object that we construct. So the collection of all such objects, using this as your rules, if you have two such objects, if you add them, it's the same as adding the corresponding coefficients here. And if you multiply them by a scalar, it's the same as multiplying each of the coefficients by the same scalar, right? So under these two operations, these objects will form a vector space. So when you see U and V here, the objects, this is what the objects will look like. They're all like this. This is now the compressed form of this thing. So any objects in the set that we want to work with will look like this. And when you want to add them, you just add the corresponding coefficients. If you multiply them by a scalar, you multiply every scalar in that expression by this scalar lambda. So these two operations will turn this set of objects into a vector space. So these coefficients are from the field F, and the elements G are from the group G, right? So we call this the natural basis. This basis G1, Gn will be called the natural basis of Fg. So our set will be denoted by this F, the field we are working with, and G for the group. So Fg. Here's an example. Our favorite example is a cyclic group where you have the elements E, A, and A squared. You can keep it in that order as a basis, because anytime you have a basis, it's important that you retain the order. Guys, here are two examples of elements. Here, the coefficient of E is 1, the coefficient of A is -1, and the coefficient of A squared is 2. In this second one, the coefficient of A squared is 0, so on. So it's omitted. So if you add them, you simply add the corresponding coefficients. If you multiply U by a scalar, you simply multiply every coefficient by that scalar, like that. So this is So there's an alternative way to write the elements in FG. You can write them like that. If you wish. So G becomes your indexing set, and you're getting, you index these coefficients using elements of G. So for instance, if you're using EA and A squared, you will index lambda E. You'll use the index A for A, and the subscript here will be A squared. So the objects, like if you are to use this notation, this is what it will look like. Instead of numbering them as lambda 1, lambda 2, and lambda 3, use the elements as the subscripts. That's all this means. So the coefficients can be 0, and when the coefficients are 0, that term is left out. So an example is this, where the coefficient of A squared is 0. So there's something more you can do with this vector space. You can actually multiply these vectors, right? For most other vectors, there's vector spaces you may not be able to naturally define multiplication. The reason is this multiplication can be defined so that it just inherits the multiplication from the group, right? So if you have two elements from FG, if you multiply them, it's simply getting all possible products all possible combinations of the lambdas here and the h's here. Then you multiply by the product of GH. So this GH will just be the multiplication in the group, because you're working in the group. It already has some multiplication that is defined. So you extend it here. So this is interesting because you can actually multiply vectors. In a usual vector space, you can only define scalar multiplication. You can't multiply the vectors, but you can define scalar multiplication. Here we are multiplying the vectors. So if you have this, here is an example, I think. With a bit of grouping, everything comes together, right? So this one simply acknowledges, in this case, this last expression here simply acknowledges that all these multiples will not give you any elements outside the group. So you can rewrite them just as elements of a group, this G, right? So you can, eventually it ends up being a sum of the elements from the group. That's what this last bit is saying. You can look at this example. The elements in the group are EA and A squared. When you multiply them, the final one simply has those three terms only, the elements in the group. The reason for that is a closure. When you multiply any elements in the group, you don't get anything outside the group. So when you put the like terms together, eventually you end up with just three terms in this sum, because there are three elements in the group. So that's what this last bit is trying to show. If you follow this, there will be some repetitions. When you're doing, for example, here you have repetitions. You have 5A and half A appearing. So you have to combine this. If you combine this, then you just have one term for A and one term for each of the other elements in the group. So this fancy notation is just to emphasize that eventually you end up with a sum of multiples of elements of the group with no repetitions. So this set FG that we defined earlier FG made up of those elements. This FG is made up of elements that we said look like this, as one way of representing them. Sorry, it should be small g, not capital. So you create elements that look like this. These are the elements that will be in this set FG, along with this multiplication, where you multiply the vectors in this vector space. So that now gives you a new structure called a group algebra. So the vector space we define like that. We define the addition and scalar multiplication, which makes it a vector space. If you like, you can check the other properties of a vector space, but I think they are easy. They are straightforward to check. But the important thing was to understand, to define the scalar multiplication and vector addition. Now, the additional structure that you can add is vector multiplication. You multiply those vectors. And once you're able to define some multiplication where you multiply the vectors and still get another vector in the same vector space, then we can say we have a group algebra. So you need FG with its vector space structure plus this multiplication of vectors, where we define some multiplication of vectors where V and R are from FG and their product also in FG. Once this is done, then this structure is what we call the group algebra of G over F. Is that making sense?
Yes.
So these are just some properties. If you have elements from the group algebra, they will satisfy these 7 properties. You can run through them later. Make sure you run through them. So remember, we have said FG can be thought of as a vector space. So you can define this assume the number of elements in G are n. So the dimension of the vector space also will be the number of elements in the group. So this FG will be a vector space of dimension n, because each element in the group is treated as a basis for this set or this vector space. It's treated as a basis vector. So if you have any elements from this FG, U and V, remember V is taken as this set FG that we constructed earlier. Pick any scalar from the field F and any pair of elements from the group. We have VG in V. So we just do the multiplication we define here is the same. Let me explain this. So since V is made up of things like this, lambda 1 times the identity. Now, the reason when we're working with the regular FG module, it makes sense to use the letter E for the identity element. The reason for that is since we are multiplying this by scalars, it becomes a problem now when you have to multiply by 1 and then you're using the symbol 1 again for the identity in the group. So this takes care of that problem. So there's no confusion. So when working with the regular FG module, we have used the symbol E for the identity of a group instead of 1. Suppose we work with this small group. So VG will be simply the same as multiplying two vectors, where G is the vector made up. G will be some vector. G is actually an element of G, the group, capital G. Problem is when you're speaking, you can't pronounce the capital differently from the small letter, but I think I'll write it to make the distinction. So VG will be the same as this. G can be any one of these elements, E, A, or S squared. So let's assume it's one of them, V. So we can get VA. VA will simply be what? It will be lambda 1A plus lambda 2A squared, because now you multiply everything in there by A. So this was VA. I've deleted this accidentally. So you multiply everything in here by the same A squared, and this was lambda 3. A cubed is just the identity. We are working with our group of order 3. So this is how you define the multiplication of this. Is V as a vector. So V is an element in FG. And A now is an element from your group, G. A is in G. But A can also be thought of as an element in FG, where the coefficient of A is 1 and all the other coefficients are 0. So when you multiply them, this multiplication turns this vector space into an FG module. So now there are two uses of FG. Here we have FG, where FG is just a set consisting of these linear combinations of the elements in the group. Then this equality, then at that point is just a vector space. So if you include now this multiplication, then this vector space becomes an FG module. Then V now is an FG module. Remember FG module definition earlier? It's an FG module. And the name of that FG module is a regular FG module. So this will be satisfied definitely. With the multiplication defined earlier, this same multiplication that we defined, these 4 properties will be satisfied, 5 properties will be satisfied, and therefore this will be an FG module. So the set FG as a vector space is also an FG module with this multiplication. It's making sense?
Yes.
Okay. So this just defines this is formally putting down the definition. So this is called a regular FG module. And remember, anytime you have an FG module, you can construct a representation out of it, because the FG module induces what is going on? A linear transformation from an endomorphism of a vector space to itself. And that endomorphism for every element in G. Someone whose microphone is on, I think. I'm getting an echo. I think now it's fine. Yeah, so this representation that you construct out of this FG module. Microphone is back again. So that representation is called a regular representation. So maybe the important thing to note is that the dimension of the regular FG module as a vector space has dimension, the number of elements in G. In our case, we'll be working with finite groups, so the number of it will be always be a finite dimensional vector space. So this also says that the regular FG module is faithful and as a proof. So the only element that fixes all the vectors is one, so that makes it faithful. So here is an example. We have our cyclic group of order 3. The elements in FG, the vector space FG, will look like this. The only thing you vary are the coefficients to get new elements. So let's see. This is interesting. So if you have a vector, if you have any vector, so any vector VA, let's pick A because A is going to be more interesting. We will this is what will happen if you get VA for any vector V in our regular FG module. You multiply it by A, this is what you will get. After rearranging, this is what you end up. Lambda 3 becomes a coefficient of E, lambda 1 and lambda 2. Now, what you need, the matrix that represents this is a matrix that acts on coefficients. So you need a matrix A. Matrix that we're looking for is a matrix A, which will pick these coefficients. Remember, we work on coordinates when we are getting the matrix. So the coordinates of the vector that you want to map are this lambda 1, lambda 2, and lambda 3. So you need a matrix A multiplied by these coordinates. Remember, we're using row vectors. That's why we multiply our vectors on the left. If we change the notation to work with column vectors, then we'd have to write the whole book and change a few things. So remember, our vectors are row vectors, so the multiplication will be on the left. When you're working with linear transformations before, I think you used to, I'm not sure who taught you linear algebra, but I think this is how you would write the, and if you're multiplying by a matrix, since it's a column vector, usually you would have that. In this case, it's reversed, the order, because you're working with row vectors instead of column vectors. So we need this matrix A, which will act on the coordinates of the vector V and give me the coordinates of the image, right? So this should, the answer after this matrix acts on the coordinates is to give me the coordinates of the image, which would be lambda 3, lambda 1, and lambda 2. So which matrix can alternate this? It has to be a permutation matrix, a matrix that permutes them. So when you multiply this by the first column of A, you should get lambda 3, right? So it means the first column should be 0, 0, 1. Is that correct? If I multiply this by the second column of A, I should get lambda 1. So that means I should have 1, 0, 0. If I multiply this by the third column of A, I should get lambda 2. So I need this to be 0, 1, 0. So that is this matrix here. So this one now requires you to fully understand how you get the matrix of a linear transformation. The matrix of a linear transformation acts on the coordinates. So by just paying attention to the coordinates, you're able to see the matrix. Is that making sense? So you can do the same for A squared. Because this gives you the image of any vector V. So for any vector, I can multiply by a matrix A, and it will shift the coordinates like this. This is so essentially this now gives you the regular representation. These matrices now give you the regular representation. This map where E is sent to this matrix, A is sent to its matrix A squared. If you had a larger group, you'd have more matrices. And this now gives you a representation of G, which we call the regular representation. So then the next thing is you can have FG itself, think of it as a vector space, and then any other FG module. Okay? Not the regular one, any other FG module. So how do we simplify this? For an FG module, usually define this as a multiplication, where G is just from G. So now what is happening here is you extend this to V multiplied by R, where R are supposed to be elements of a set FG. Just FG, the set, the vector space FG that we defined earlier. So now here we assume that FG is acting on the FG module under this multiplication. So that multiplication is defined here. If you have an element R from FG, the group algebra, and any other element V from some FG module. We don't care what's the FG module here. It can be any FG module, because as long as you have the FG module, this multiplication is defined. And since R is just made up of elements of G, we can define VR as where V simply acts on G. So what you get here is an element in the FG module, because it's just that VG is, remember VG will still be in our FG module, right? So VR will give you another vector as well, because it's just a linear combination of vectors. So this thing is a vector in V. So we have extended this from the multiplication VG. Now we let the whole FG all of FG as a vector space, act on any FG module and define that multiplication like this. So this, I think this makes sense. So you can go through these examples on your own. See what that means exactly. So, but if you're working with a regular FG module, then that product is just the same as a product we defined earlier of any two elements from the regular FG module. So again, there's a list of properties. You should verify that all these hold. I think the only one that is maybe problematic is covered in the book. That is part 2. The rest, you can try to write them out. Like I said, once you write them out, if you have a problem, if you feel there are gaps and you want them covered, you can let me know. You share what you have written, then we can look at it. So that covers chapter 6 of the Constitution. Again, you have a whole bunch of exercises for practice at the end of every chapter. So please do not ask me for practice questions. You have more than enough. By now, you should have done some of them. Try to solve all this. And the answers are at the back. If you have problems with your solving them, the answers are at the back. I think we can stop there for today. We had covered a bit of this homomorphisms last time. I think I'd left you some work. We even got to this point of direct sums, yes. So this we had covered a chunk of it. So the only thing that we have not, we can start from here next time. We covered only part of it up to here. This is what we covered, but you can extend it to, would the direct sum consist of more than one term? You can extend that to a more general situation. So we can start from there next time. Then there are some 2 theorems here. But these are important theorems. So if you can read them, read them. Otherwise, we look at them next time. So we'll start from here. Direct sums. Any questions?
Excuse me, sir.
Excuse me, sir. Excuse me, sir.
You're excused.
You're excused. You're excused.
Sorry, let me remove the echo. Okay, I was requesting when you're done with the first chapter, you kindly send so that we can start perfecting it kabisa based on your summary.
It's not really a summary. It's, well, it's a little shorter than the book, but it's not quite a summary. It has some detail, but I will share.
Okay, so thank you.
Allow me to do that later today.
Okay, thank you.
Or since tomorrow is a holiday. You can do that tomorrow
Okay,
and
thank
share.
you.
It actually needs your full attention and a lot of practice for these things to stick. They use a lot of ideas that you've learned from previous courses rather casually. So the assumption is that you have a mastery of those other concepts. I will stop the recording now.